Now let's consider the derivatives of exponential functions. So if we have f of x equals a to the x, and first of all, if we go back to the limit definition of the derivative, we would have the limit as h approaches 0 of f of x plus h minus f of x over h. So in the case of an exponential function, it's the limit as h approaches 0 of a to the x plus h minus a to the x over h. Now we could use rules of exponents, and you're very familiar with if we had x squared times x cubed, that would be x to the 2 plus 3, or x to the 5th. So what if we had it like this, and we're going to go this direction with it? So we have a to the x plus h, so that can be expressed as a to the x, a to the h, minus a to the x, x over h, and the limit as h approaches 0. We can now factor out the common a to the x, and because we are taking the limit as h approaches 0 and this a to the x does not involve an h, we can actually move that function outside of the limit and multiply that function later. And so we are now looking at the derivative of this a to the x is a to the x times the limit as h approaches 0 of a to the h minus 1 over h. Now this is not something that we can directly evaluate, so let's kind of have a look and consider something that maybe we can do. Let's figure out this derivative at x equals 0, and we would have a to the 0, which is 1, and then be left with the limit as h approaches 0 of a to the h minus 1 over h. If the function a to the x is differentiable at 0, then we have that it would be differentiable everywhere, and f prime of x would equal, because we could replace this piece with f prime of 0, it would equal the derivative evaluated at 0 multiplied by the exponential function. So essentially what this is telling us is the rate of change of an exponential function is proportional to the function itself, because its derivative is the function itself and then multiplied by the derivative of the function at 0. So the slope is proportional to the height here. Now let's see if we can get a sense of what this limit as h approaches 0 of a to the h minus 1 over h would look like. And so let's look at a table of values, and we can choose h and let h approach 0 here. And we picked a equaling 2 and a equaling 3, so we could see if this limit appeared to exist. And we look here as the a equals 2, we can see as we let h get nearer and nearer to 0 that this appears to be approaching a value of about 0.69. We can see if we let a equal 3 and we look at the limit as h approaches 0 that this appears to be approaching a value of about 1.1. It does appear to have the limits exist, and they would depend on this a. And now the simplest of these would be if this particular limit equaled 1. So the slope of the tangent to the curve when x equals 0, if that value was 1. We have the two derivatives for 2 to the x and 3 to the x, and if we looked at those graphically, we can see that this value here is less than 1 for 2 to the x, greater than 1 for 3 to the x. And so if we wanted a slope of a tangent that would equal 1, we can see that it would have to be somewhere between 2 to the x and 3 to the x. It looks like a little closer probably to 3 to the x. So could we find an a so that the tangent line equals 1? And the answer is yes, and in fact that function is e to the x. Now we've run across e to the x before in college algebra, and basically at that point you just learned how to work with it. We didn't necessarily have it officially defined other than to say if you need to compute those values, we essentially used a calculator. Well, we are going to look at this base e. We're going to define this to be the number such that the limit as h approaches 0 of e to the h minus 1 over h equals 1. So we're saying at 0 the slope of the tangent to this curve of this number e to the x would equal 1. Now we are later going to define e to the x in terms of a limit, and then in Calc 2 in terms of an infinite series. Right now we have this definition based on this limit that we have gotten as we were trying to find the derivative of an exponential function. E actually is an irrational number that continues on and on and on, and here are a few of the digits of e. The derivative of an exponential function is a to the x times the limit as h approaches 0 of a to the h minus 1 over h, and if the a happens to be e, then we know that this equals 1, and so here we would have the base of e to the x multiplied by 1. So the derivative of e to the x is e to the x. The slope at any given point x is the function value itself, e to the x. So if we computed e to the 0, we would get 1, and the e to the x is the special curve whose slope of the tangent to the curve at 0 equals 1. Now we're going to return to other bases besides e in a little later section, because we did come up with that formula for the derivative of a to the x, and it was the exponential function itself, a to the x, but then multiplied by this limit that we just kind of looked at in terms of a table. And a little bit later, when we have a few more tools, we will see how to actually compute what that number was. We know for 2 to the x it was 0.69 approximately, and for 3 to the x it was approximately 1.1, but we will have a way of computing that a little later. So the only thing that we need for this particular section is the fact that the derivative of e to the x is e to the x. The constant e was identified and named by the Swiss mathematician Leonard, I don't know, I didn't get his last name in there, Leonard Euler. So it's also called Euler's constant, and here's Euler. He lived in the 1700s, very prolific mathematician, did a lot of work and responsible for a lot of our notation, and we use his little e to signify this particular limit as h approaches 0 of a to the h minus 1 over h equaling 1. So let's see if we can find the derivative here of this particular function. So the derivative f prime of x equals, looking at our rules, this is basically a constant multiplied by a function, so we can take the derivative of this function, the derivative of e to the x is e to the x, and then multiply the constant. And then here we have a power rule, power out in front, decrease the power by 1, and then multiplied by the constant, and then we have the difference, so we could take the difference. So our derivative is just 4 e to the x minus 6 x. Well, what if we wanted, now remember when we put this in parentheses, we know that means the derivative, so we want the 100th derivative of f of x equals e to the x. So our order of derivative is 100. If we took the first derivative, it would be e to the x. If we took the second derivative, it would be the derivative of the derivative, so it would be the derivative of e to the x. So it would be e to the x dot dot dot. So we know that the 100th derivative of e to the x is also e to the x.